So if instead we choose u to be the second factor over here, e to the x over 4, then what is u prime? According to the chain rule, e to the x over 4 is the derivative of the outer function times 1/4, yeah, times the derivative of x over 4. So where we had to use substitution to take its antiderivative, we had to use the chain rule to take its derivative, because those are alter egos of one another. Okay, so if we pick that for our u, then what does that make our v prime? X. And if v prime is x, then what is v? Yeah, x squared over 2. All right, so there are our pieces when we made this set of choices. And now again, running the integration by parts formula, we're supposed to get u times v minus the integral of u prime times v. So, what do I have here? U is going to be e to the x over 4. V is 1/2 x squared. So that term is okay. The second term, we're going to have to take the antiderivative of u prime times v. U prime is 1/4 e to the x over 4 times x squared. So does this change your opinion about the two substitutions being equally, well, they're equally valid, right? Because this integration by parts formula still works. We still know that the integral we started with is equal to the expression we end with. But what's the problem with this?
We have to do it again.
Yeah, we have to do it again, right? And if we made the same choice again, u equals e to the x over 4 and v prime equals x squared, then when we did it again, we would end up with an integral down here that had some stuff in it and an e to the x over 4, and then when we took the antiderivative of x squared, we would end up with an x cubed in here. And we would have to do it again. And if we did it again like that, we would end up with an x to the 4th times e to the x over 4, and we'd have to do it again, and again, and again, and again, and again. And that would be a process that would never end, because we're not making our integral any simpler. So that's what I mean when let's think about strategy. That what does it look like to make choices that are as efficient as possible to make our integrals simpler rather than more complicated. So x was a great choice for a u, because if we took enough derivatives of it, in fact it only took one, it became a constant. So does anyone know what kind of functions we're talking about, who, if we take enough derivatives of them, eventually become constants? A polynomial function. Polynomials. Or if you like, we could call them powers instead. Anytime you have powers of x, that's a pretty decent choice. So that's a pretty good choice for u, because eventually if we take enough derivatives of it, it's going to go away. Other good choices for u are functions which change their stripes to something simpler when you take their derivative. For instance, what's the derivative of natural log of x? 1 over x. And if our choice is between taking an integral with natural log of x in it or taking an integral with 1 over x in it, which one's easier? 1 over x is a lot easier to deal with than natural log of x is, because it becomes a power of x. So a really good choice for you is logarithmic functions. Because as soon as we take one derivative of them, they're not logarithmic anymore. They're just powers of x, namely x to the negative 1 in the case of ln. Right? So that's a great choice for you. Another great choice for you is one that we haven't really explored yet. Maybe you did a little bit in Calc 1. But inverse trig functions, arcsines, arccosines, arctangents, is another example of functions which, when we take their derivatives, they change their stripes. So, for instance, does anyone remember what the derivative of arctangent of x is?
This
1 over.
1 over tan x.
That would be cotan, not arctan. Yeah. Either way, yeah, Greg's got it. 1 over x squared plus 1. Yep. That's the derivative of arctan x. Use an integral table if you don't remember that. Which means that as soon as we take the derivative of arctan, it's no longer an inverse trig function. It's no longer a trig function at all, which should be great news for everybody, right? It's just 1 over x squared plus 1. So those are great choices for you as well.
What did you say was these arctan functions again, these trigonometric functions?
Meanwhile, we also chose some things that were fairly easy to take antiderivatives of. Even if we did need to do a substitution, the exponentials are really friendly to take antiderivatives of because they don't really change. Right? They just stay e to the whatever. They just might spit out a constant at you. So exponentials tend to be good choices for v. You could use them for u's as well, but if anything above them on this list is there, that's probably a better choice for you. And then finally, the forward trig functions, sine, cosine, and tangent, especially sine and cosine, are pretty easy to take antiderivatives of. Antiderivative of sine is minus cosine. Antiderivative of cosine is sine. So because those are fairly simple to take antiderivatives of, we tend to pick them for v. And this creates a little acronym, LIPT, that people occasionally will use to try to decide what to make what in integration by parts. So you want to find your u's as high on the list as possible and find your v's as low on the list as possible. So when we're looking at x e to the x over 4, we're going to say, well, we've got one piece, the x, that belongs in the p category, and we have another piece, e to the x over 4, that belongs in the e category. And so when we're deciding which to make which, we just take the top one to be our u and the bottom one to be our v prime. And generally, following this strategy tends not to get you into too much trouble. So that's LIPT. That's the first little mnemonic for the day. So here's a new integral. And I'd like to do this one using the by parts formula. So first we have to make our choices. What's a good u? And what's a good v prime here? So let's classify our pieces. Where does the x squared piece belong? In LIPT. Yeah, it's a power of x again. Where does cosine x belong? Trig. A forward trig, so it's a t rather than an I. Right? So, what shall we choose for u in this integral? X squared, because it's higher on the list than the trig function is, so that v prime is cosine x. So how I'm going to organize our work here, I'm going to do it for the following reason. Let's just have a little bit of foresight. If we were to look ahead at what integration by parts would do for us here, integration by parts would give us that this integral is equal to, u times v minus the integral of u prime times v. And if we chose x squared to be u, then what's u prime? 2x. So here's u prime. And so our integral here would have a 2x in it, times probably some trig function. But then what would I have to do in order to evaluate that integral? I would have to integrate by parts again. And so that would require us to go in here and maybe surround this integral with some parentheses, and then use integration by parts to figure out what belongs in those parentheses. And that's going to be, again, some u times some v minus the integral of some u prime times v. And if we chose the 2x to be our u one more time, then the derivative of 2x is a constant. And then we probably could do that last integral without integrating by parts. But here's an example where we have to integrate by parts twice before we get something that we no longer need integration by parts for. And that's a lot of times where sign errors creep up. So here's my proposal. I just back us up a little bit here. my proposal is let's keep track of, as long as we're making the same choices for u and for v prime every time. In other words, as long as we're always choosing our u to be that power of x, and as long as we're choosing the v prime to be our trig function, then the first time I integrate by parts, x squared is going to turn into 2x. And then the second time I integrate by parts, 2x is going to turn into 2. If I were to integrate by parts again, I would end up with the derivative of 2, which is 0. So that's why that's a good choice for u, right? Is that eventually, if I take enough derivatives, and that's what I'm doing here in the left-hand column, if I take enough derivatives, I eventually end up vanishing. So in this little organization, we're taking derivatives down the left-hand column. In the right-hand column, meanwhile, if I'm always making the same choice for v prime, what am I doing on the right-hand side? Taking antiderivatives. So what's the antiderivative of cosine of x? Yeah, careful about that SIGN sign. Antiderivative of cosine is positive sine, going counterclockwise around that little clock. Then what's the antiderivative of sine? Yeah, there's where our minus shows up in the antiderivative, minus cosine x. Then the antiderivative of minus cosine x. Yeah. And if we were to keep going, this pattern would just keep repeating. So what this method does is it organizes all the derivatives and the antiderivatives that we're going to need all in one place, right? So that we don't have to recursively apply this formula. And if we were to use integration by parts once on this integral, I would end up getting a product of 2 factors. I would have u times v, and u times v would be x squared times sine of x. We had to go one step of antiderivatives before I found my v. And so my first term here would be x squared times sine of x. X squared sine x. After that, I would have minus the antiderivative of u times v prime. And in our table, u times v prime, sorry, u prime times v. That's backwards. U prime times v. And that would be that horizontal product in the table right there. 2x times sine of x. And so this little horizontal line here has an integral sign attached to it. So that's the first step on how to use this table, is just go draw a diagonal line starting from the top, and that product becomes part of your antiderivative. Then draw a horizontal line with an integral sign on it, and a minus, I suppose, and that becomes the second piece. But then if we're going to use integration by parts on that product, we just do the same thing again. And instead of having that horizontal line there, and the integral sign there, let's just repeat. Let's draw a diagonal line going this way, and that will be the first term of my second integral by parts. Except that because there's a minus sign out in front of that integral, this line we'll put a little minus on to remind us that what we have in our product is not really the product of 2x and minus cosine of x, but the opposite. So I end up with a plus 2x cosine x. Cosine x. And then if we were to go one more step of integration by parts, we would have minus the integral of this, but with a minus in front of it from our original minus. So this would actually have a plus sign on it and an integral. So I could, over here, write plus the integral of 2 times minus cosine x. But instead of that, let's continue this process one more time and integrate that by parts, even though we wouldn't have to, because it's fairly simple. But if we integrated that by parts, we would begin with this diagonal product with a plus sign on it, minus the integral of this horizontal product, except that this horizontal product is what? So all told, what do we get using this method? Looking back at everything, we now have all of our integration done, and all the products of the terms that we need are the diagonal products along these lines over in the table on the right. So our total integral at the end of the day is x squared times sine of x. That's the first product. Minus the second product. And the second product was 2x times negative cosine x. So we end up with plus 2x cosine x. And then our final product is plus the product of 2 times negative sine x. So that's minus 2 times sine x. And if we were to keep going, we would write plus 0. So let's not, and say we did. And then all I need is a plus c. I'm done. So the point is, I did a lot of talking about this, but the method that you can kind of take to the bank, if you will, as long as you're always making the same choices for u and v, this table method of integration on the right will get it done. Just take the derivatives down the left-hand column, antiderivatives down the right-hand column, draw in the diagonal lines as far down as you need to. If you ever stop and draw a horizontal line, it gets an integral sign on it, for whatever reason. But if we're starting with a polynomial like x squared, eventually you're going to get to 0. And so there's no need to stop. Just keep going until you would have gotten to that 0. And then just put alternating signs, starting with plus, then minus, then plus, and so on those diagonal lines. And the products along those diagonal lines form your antiderivative. So it's almost a black boxing of the integration by parts formula. It doesn't get you off the hook of knowing the formula, but it does, I think, help to organize all these derivatives and antiderivatives in a way that avoids as many errors as possible. My students actually taught me this. This doesn't appear in many books. But I think it's a really slick way of organizing your thoughts in integration by parts.